Hello, class. This is Mr. Hart, and this podcast we're going to start a unit on energy, work, and power. Now, you may have heard of some of these words before, and you may have an intuitive sense of what they mean, but we want to get down into what they mean in a physics sense. They have very specific definitions in physics, and they're very powerful concepts we can use to solve for motions of objects and things like that. So let's get right into it and start thinking about what is energy. Okay. What does it mean for an object to have energy or to use energy? Okay. Now, when I say energy, you may think of something like a light bulb, or maybe you think of lightning, or maybe the blue lightning stuff that the Emperor shoots at Luke in Star Wars, or whatever it may be. But a lot of people think of energy like a fluid, okay, something that kind of flows from objects. And that's not necessarily the best way to think about it. Okay, it turns out energy is purely a mathematical concept that we use in physics, kind of like force was. Now, we can associate it with things like a push or a pull with force. Energy, we can associate it with light and other stuff. But when it comes down to it, it's just a mathematical quantity we use to describe movements, describe motion, stuff like that. So to get a purely physics definition, energy can be described as the ability to do work. Well, what is work? Work is the ability to move an object with a force. Okay? So, if work is the ability to move an object with a force, and energy is the ability to do work, we can think of energy as a storing mechanism. Okay? We're going to store energy in something so that we can move it later. Okay? Think of like a car engine, for example. There's energy stored in the gasoline. You're not going to use it right now, but when you start your car and you start to use the gasoline, then you'll start moving that object forward. Okay, so think of energy as this kind of stored movement. We're going to use something later that we'll then use to move an object. Okay, so don't worry right now. I mean, it will come as we go through some examples and think more about these concepts, but we want to think of energy purely as this ability to do work. Okay, so let's think of some example scenarios. Okay. So let's say you have to push an object up a ramp. Okay, you have to push this box up a ramp. You have to apply a force to move it. So you are going to do work on this object. Okay. Well, how much work are you doing? How much work is needed to move this object? Okay. Well, we can describe that with this equation. Okay. So work will represent with capital W. Okay. And work is simply equal to the force that we use to move the object times by the displacement of the object, how far we move it. Displacement. Okay. So how much force we're giving to the object times by how far we move the object is equal to the work that is done on the object. Okay. And the key concept here is that this always has to be in the direction of the force. If we move an object in a different direction, that doesn't really count as work done on the object because it wasn't the same direction as the force. We'll get to that later, but keep that in mind. So just how far we move the object in the direction that we moved it is the work done. Okay. Let's think about units on this. Okay. What are the units of work? Well, we have a force that we know is in newtons, and we have a distance or displacement, which we know is in meters. So our unit is going to be newtons times meters, which is what we'll call a joule. Okay, so capital J is a joule, and that's the units for work and energy. Okay, so work is the force times the distance, and the amount of energy or work that is done is measured in joules. Okay, so let me ask you a question before we go into some example problems. Let's say your car is stuck in the snow, and you're pushing and you're pushing and you're pushing on your car, but it's not moving. Is any work done on that object? Okay. Now, if you think just purely from the mathematical definition, hopefully you realize the answer is no. If you're not moving any distance, right? We said work equals force times the distance traveled or displacement, right? If change in x is 0, then your work done on this system is 0. So this is where we got to separate kind of the English definition from the physics definition. Okay. In English, you would say, yeah, well, those people are working hard. They're pushing really hard. They're doing a lot of work. Okay. That's kind of an English term, right? But in physics, work has to actually move the object. Okay? If you don't move that car, then you're not doing any work on it because you didn't change how much energy it has. It's still sitting there. It's not moving. Okay? And so you're not doing any work. Okay, so separate that in your mind. There's English work and there's physics work. Physics work you have to move in order to do work. Okay? So let's look at an example problem really quick. Okay, a woman pushes a crate a distance of 5 meters with a force of 800 newtons. How much work did the woman do on the crate? Well, hopefully this isn't too difficult. We know work is force times the change in x. Okay? Force is 800 newtons. Okay? The distance is 5 meters, which gives you a total of 4,000 joules. Okay? So pretty straightforward calculation. Just take the force times it by the distance. Okay? But be careful when you read these problems. I see a lot of students fall for this problem right here. Okay? A man lifts a 20 kilogram box. He lifts it 2 meters into the air. How much work did he do on the box? Okay? Well, work is force times distance, or displacement. Okay? The displacement is 2 meters. What is the force needed to lift that box, though? A lot of students will just say, oh, I see a number, and they'll put 20. But that's not the full story, right? It's 20 kilograms, but the force is the weight of the box, right? You have to match the weight of the box. Okay. So let me give it more space. So it's 20 kilograms times 9.8 meters per second squared. Okay. That number is equal to the force because that's the weight of the box. So be careful when you're going through these problems. Don't read them too fast. Okay. And then that times 2 meters. Okay, so our force is 20 kilograms times 9.8 meters per second squared, and our distance is 2 meters. Okay, then we times those all out. 20 times 9.8 times 2, and we get that is equal to 392 joules. Okay, so pretty straightforward stuff. So all you gotta do to calculate it is just take the force times it by the distance. Okay. So let's think a little bit more about what it means to do work and what energy is and all this stuff. Okay? So let me give you an application to think about. Let's say you are shooting a rifle. Okay, you're going hunting or something like that, and you want to be very accurate, okay, with your gun, and you want, hit the target, whatever it is. The question is, do you want to have a longer barrel or a shorter barrel? Okay? Which one will be more accurate as far as a shot? Now, intuitively, you hopefully know that the answer is a longer barrel. The longer the barrel, the more accurate the rifle. But now we have a little bit better sense of why that is. Okay? If you think about a rifle or any type of gun, the bullet has to travel through the entire barrel, right? So for this rifle, it'd be this whole distance. For this barrel, it would be this whole distance. Okay, this is our change in x. Okay. So, if the bullet is ignited, right, there's that little piece on the back that ignites, causes the explosion. Okay, as long as the bullet is confined to this barrel, okay, it keeps the force being applied throughout the entire barrel. Okay. So, if the force is the same in both cases, you're using the same bullet with the same explosive powder in it, which one's going to be more accurate? Well, whichever one did the most work on the bullet. Okay, so you have the same amount of force in both cases, times by different amounts of change in x. This one will have a much larger work done on the bullet than this one. Okay, so this will be a more accurate rifle. Okay, now there's a lot of other things that go into play, but generally speaking, that's the main cause for accuracy in guns is how long the barrel is, because it's how much work can be done on the bullet, which determines how much energy it has, which relates to how accurate it is. So let's think more about energy. And again, I talked about energy as this idea of being able to store a movement for later or store some type of operation for later. Okay? Think about a battery or gasoline, for example. Okay? Let's say you have a little toy car, you put some AA batteries in it, you press a button and the car moves. that battery is responsible for the movement of that car. It's going to do some work on it. It's going to apply a force over some distance. Okay? So in order to do that, it had to have that movement stored somewhere. Okay? Well, it's stored in the chemicals in the battery, which we can call energy. Okay? There's not some physical substance of energy in the battery. The chemicals in there can go into what we call energy. Again, I want to make sure it's clear. This is a mathematical concept. It's not like some fluid or something. But the chemicals themselves are storing energy, which can later be used for movement. Same thing with gasoline. You have some chemicals in there that you can cause a reaction with, and then when that reaction occurs, it causes motion. So we can think of that chemical as having energy stored in it that we can use for motion later. Okay? So there's actually a whole bunch of different types of energies. Okay, there's gravitational energy. Okay, there's chemical energy. There's elastic or spring energy. There's electrical energy, and there's thermal energy. Okay, and if you think about all of these, they can cause something to move, right? They can cause work. So if you have gravity, right, you have a big cliff and you push something off the cliff, well, the gravity is going to start moving that object. So you can think of that cliff as having stored energy. Once the object moves off, it will begin to move. Okay. Chemicals can have energy like we talked about. Once the reaction occurs, they release energy which causes a movement. Springs have that stored energy because you compress them. They'll want to decompress. Their shape causes a movement. Electricity and things like batteries and other things, you can give electricity to an object and it will cause a movement. And then, of course, heat and thermal energy. If you heat something up like water, it can cause boiling, which can cause movement. Okay. So again, think of all these things as storing an energy, storing movement for later. Okay? We'll cover this a whole lot throughout this whole unit. Okay, so let's just focus on one simple example for right now. Let's think about gravitational energy for today, and then we'll move on to other types of energy later. Okay? So let's think about this gravitational potential energy. Okay? So you have a big boulder sitting on a cliff, or some type of book or binder sitting on a shelf. Okay? If you can move that thing so that it will start to fall, right, it will begin to move, right? Gravity will do work on the object and begin to move it. So you can think of the object having the stored energy simply because of its position, of how high it is on the shelf or how high it is on the cliff. That's storing some energy because it could fall and then begin to move. Okay? So how much energy is stored? Well, we use this equation to describe it. Okay? So we're going to call potential energy PE. Okay? That's not physical education. That's potential energy in this class. Okay? And in this case, sometimes you'll see me subscript it with a lowercase g, just to make sure it's clear that this is gravitational potential energy. But that is equal to the mass of the object times the gravitational constant we've used before, gravitational acceleration. In this class, it's 9.8 times h, which is the height, or how high the object is off the ground. Okay? Anything about this makes sense, okay? A big boulder is going to have a lot more energy than a small book, right? It's going to move with a lot more force, okay? Gravity is going to be the same in every case. And then, right, obviously, if you drop a book from 1 meter up compared to 10 meters up, one's going to have more energy than the other. Okay, so this is our equation for describing how much potential energy an object has. Okay, so let's do an example problem. So let's say you have this big rock. It's 350 meters up from this cliff, and we're trying to determine how much energy it has, how much potential energy it has. Okay, well, we know potential energy is equal to mgh. In this case, that's 150 kilograms times 9.8 meters per second squared times the 350 meter tall cliff. Okay? So again, we're just timesing those all together. When we put that in our calculator, we get that the total potential energy of this rock, if it fell, right, it's kind of storing this energy, okay, is 514,500 joules. Okay, so again, we measure it in joules, just like we did with work. Okay, because it's just newtons times meters in every case. Okay? And so that doesn't mean a whole lot right now. When we get to conservation of energy, this will be a lot more useful, but we're going to be able to use these energies that are stored to calculate how fast objects are going to move, how far, things like that, based on these quantities that we represent. Let me give you one more thing to think about with this, and this is a key idea, okay? And that is that work is the transfer of energy, okay? So if you move an object, you are giving energy to that object. You are giving it stored energy that it can use later. And likewise, when you use energy, that energy can do work. So let's look at this problem to see what I mean. So let's look at that problem we did before where we calculated the work of a 20 kilogram box lifted 2 meters into the air. How much potential energy does it have? Okay, so this time we're calculating potential energy rather than work. But notice something interesting. If we say potential energy equals mgh, well, that's just going to be equal to 20 kilograms times 9.8 meters per second squared times 2 meters. And if we times those all out, you'll notice that we get the exact same answer, okay? That this is 392 joules of energy, okay? So, if the man does 392 joules of work to lift the box up, now the box has 392 joules of energy stored in it. So when he drops the box, it will release that energy and do work again and move the box back down. Okay? So there's this very strong connection. I can do work to give something energy, or I can use the energy to do work on something else. Okay? So they're very, very connected. And again, throughout this unit, we'll see this a whole lot of this connection between work and energy and this transferring of energy. Okay? And this is often why people think of energy like a fluid or something, because it does transfer between all these objects. But again, it's just a mathematical concept, this mathematical construction we can use to think about motion. Okay? We'll see this more next time. But for now, go ahead and do the homework assignment. Okay? Work in potential energy. Again, really straightforward homework. But let me know if you have any questions, and thank you for watching.